Hi, ladies and gentlemen. Hello and welcome back. Hope you enjoyed the introduction session. We are now moving on to a little bit more technical side of things. So we're going to look at an intro, an introduction to data analysis. And here we're really going to look at or start to look at how we're going to use data to answer research questions. So you can really think of this session as an introduction to empirical finance. Remember we said that empirical finance, or in empirical finance, we are going to give you tools to use in order to take data, analyze data, digest data, in order to get to a research answer. So we're going to give you, teach you techniques of how to process data relevant to what you want to study in your research. Okay, so in this session, we're really just going to dig into the basics of what data is, the different types of data that we get, basic data analysis methods, and this will then be used as a base for the upcoming sessions that we'll have in empirical finance. Okay, now what we are going to do in empirical finance is we are going to use a data analysis package or an econometrics package called eViews. And so we're going to use eViews to help us do our data analysis. And what this affords us is to do complex mathematical and econometric statistics and run complex mathematical models without actually having to do the econometrics and the mathematics behind the methods that we apply. Okay, and so of course, in order for us to use eViews, you need eViews on your computer. And so I highly recommend that you purchase the eViews license. I'm going to send out a link to this, but I highly recommend that you purchase it. There's a student version that's a lot cheaper than the actual license. I think it's about $50. That's a lot cheaper than the actual license that you can purchase. So of course it'll help, right? Because you're going to use this data package extensively in almost all your assignments. You're going to use it in your or when you do your exam, and then you're going to use it, of course, when you do your research dissertation. Okay, so highly recommended to purchase it. Now, with that said, all the computers in the labs on the UJ APK campus does actually have eViews installed on it. And of course, as a UJ student, you can make use of those computers. But that will mean that every time that you want to use eViews, you need to go into campus and use it there. So ideally, of course, it would be great if you do have it on your computer installed. As I've said, I'll send a link to that. Now, I'm going to start. You'll see this video is sort of split into two. You've got this video and then an introduction to data analysis part 2, just to make sure that the videos doesn't get too long. We're going to start with some basic descriptive statistics. And of course, as an example, we are going to do descriptive statistics on an actual data set in eViews in the practical sessions. Okay, so after these videos, you'll see that there's practical videos as well. So the descriptive statistics, rather than asking you to calculate it on a piece of paper, I'm going to show you how to do it in eViews. Okay, and so we will run a lot of analysis in eViews.
But this is the most basic level. It basically characterizes your data set. So it provides you with a mean, for example, an average, median, a middle point, a mode, the most frequent data point. You've got your standard deviation and variance that shows you how far your data set actually deviates from your mean. Some considers that as your volatility of your data set. Then your spread, your maximum minus your minimum value, and then your distribution, how your data set is distributed around your means, or around your mean at least. So if you think about your normal bell-shaped curve, that is a perfect distribution around your means. We're going to do a few, or your mean, we're going to do a few of this in eViews, just as an example. Now, characterizing your data set is really not something that we ever base conclusions on. It's more interesting than anything else. You're not going to use descriptive statistics as a sole method in your assignment. What we are more interested in finance and economics are relationships. Okay. Now, the first, or relationship between two or more variables. Now, the first step in this will be your correlation analysis, that tells you numerically, or provides you a numerical measure of the relationship between two variables. Let's call it X and Y. For example, market capitalization and debt. Okay. Once again, this formula, we are going to calculate the correlation between variables in eViews. So you do not need to know the formula. You need to, however, be able to identify it and describe it. So when you write up your methodology section in your study, and you use a correlation analysis, you need to write this up. You need to show me, I'm going to, or the study will conduct a correlation analysis using the following formula, and then you describe it, right? So you don't have to do the calculation by hand, but you have to be able to describe your analysis, your method. So the properties of a correlation, or of correlation, a correlation analysis, very important, right? Because this is what we're going to use to interpret ultimately our results. So firstly, R, which is your correlation coefficient, lies between -1 and 1. Okay. Positive values of R indicates a positive relationship between X and Y. In other words, as X moves up, Y moves up as well. Negative value obviously indicates a negative relationship between X and Y. The larger our R becomes, the stronger our correlation R. Okay. So the larger positive value, so if R is positive, the larger the positive value is, the stronger positive correlation there are between X and Y. Okay. R equals 1, indicating a perfectly correlated series, which is only in theory the case. You typically don't get this, except the correlation between a variable and itself. And then the same applies for negative values. The more negative R becomes, the stronger negative correlation we've got between two variables, X and Y. -1 being perfectly negative. The correlation between X and Y and X is always the same. Okay, this is important. In other words, it doesn't matter which way around we analyze our data set. It remain your R, your correlation coefficient, will remain the same. Just want to make sure it is recording. Yes. Now, importantly, the correlation between the variable and a variable in itself will always be 1, right? That makes sense. Now, these rules of thumb are quite important to remember, right? So when you interpret your outputs, you need to refer back to this. Okay, a correlation measure between 0.8 and 0.99, or the inverse, -0.8 or -0.99, indicates a strong relationship. So this is your rule of thumb. Anything between, in absolute terms, 0.8 and 0.99 indicates a strong relationship. Any measure between 0.5 and 0.79 indicates a moderately strong relationship, whether it's negative or positive, obviously. Correlation between 0.3 and 0.49 indicates a weak relationship, and anything below 0.3 or -0.3 indicates a weak relationship, where 0 obviously means there's no relationship, or 0 means there's no relationship. Okay, so remember these rules of thumb. So if you have, for example, -0.66, you'll typically say there's a moderately strong negative relationship between X and Y, whatever X and Y is. Okay. So just an example, executive compensation being Y and profit obtained being X, we've got an R squared of 0.66. So here we want to see whether if there's an increase in profit, executive compensation goes up with it. Now we've got an R squared of 0.66. What does this tell us? Firstly, it tells us that there's a positive correlation, right? Because it's not minus. In other words, it's positive. So there's a positive relationship. So as profit increases, executive compensation increases, and vice versa in actual fact, right? Because it doesn't give you causality, it only shows you a relationship, but we'll get to that. But that is in effect what it means. So companies with higher profits tend to pay their executives better. And then companies with a lower profit tend to pay the executives less. Now that makes sense, right? So obviously the more you earn, the better your compensation should be. Now, however, this is not perfect. It's not a perfect correlation. So there is some room for something else to drive executive compensation. Okay? And so this brings us to our R squared. Now R squared, very important measure. We're going to use this with our regression analysis as well. R squared, ultimately all it does is it squares our R, or takes the power of 2 of our correlation measure, and what it measures is the proportion of variance in one variable, in this case executive compensation, that explains the variance in the other, in this case profits, and vice versa. Okay, so it basically, just for example to make it simple, explains the level of which a variance in X is explained by a variance in Y. So in this case, if we square our, if we power to the 2 our 0.66, we get 0.44. Now what this means is, how this can be interpreted is, that 44% in the variation in our executive compensation can be explained by profits, a variation in profits. So 44% of the variance is explained. So this shows that a fairly large part of executive compensation gets explained by profits, but it's most definitely not everything. Okay, so there's 56% of a variance in executive compensation that's explained by something totally different, whatever that may be. Okay, so this is how we interpret it. So it's a good measure. Profit is a good measure for executive compensation, but it's not the only measure. Now, understanding correlation in terms of an XY plot, very important, because ultimately our regression analysis will be based on our XY plot. Okay, so we need to understand our XY plot. And so if we look at this is house prices versus lot size. Typically what we'll do, you should have somehow somewhere in your university career you should have drawn up a XY plot at some point, but you typically you've got a large number of houses and you correspond their price with their lot size, each house with their price and their lot size. If you do this for the range of your houses that you've got in your sample, you get something like this. So every time you correspond, you get something like this. Now from this we can derive a few things. We can firstly see that there's some upwards movement, right? So we can see, even though it's not a strong relationship, that there's some type of an upwards trend. As lot sizes go up, it seems like house prices goes up with it. So there's a positive relationship, but we can also see that it's not extremely strong, right? Because we've got a lot of outliers. And what we want for a strong correlation analysis, we want these dots to be very close to each other, in unison. If you've got a spread like this and these outliers it means that there's a weak correlation. So it sometimes moves together, but not always. So if we go and calculate the R between X and Y, so our correlation coefficient, we get a 0.51, and this typically shows us we've got a moderate positive correlation. Here's a scatter plot that reflects output that's a lot closer. So this will definitely give you a stronger correlation coefficient, and this will give you a perfect correlation coefficient. You can see there's no outliers, they move up in unison. Now, very important to understand that correlation does not mean causation. Okay, and this is why ultimately we do not only use correlation in our analysis, because we cannot say that just because they are correlated, two variables, that the one causes the other. And that is ultimately not good enough when we run an analysis. So we need to take it a bit further, and that is why we do run a regression analysis. But for now, let me explain how this, or why this is not the case. Why correlation doesn't mean causation. So if you think about two things, I'll do the example now. But if you think about two things, I just want to make sure my battery doesn't run flat, because I'm doing this in my car in order to not disturb everybody else in the house. If you think about two stocks, you think about Vodacom and MTN. If you regress, or if you get the correlation between those two variables, both are in telecoms, you'll typically get that there's a strong relationship, strong correlation. But do you think that means that MTN drives the Vodacom share price, or vice versa? No, that's not the case. There's likely some external factor that drives both of them up and down at the same time. So the one, MTN, doesn't cause Vodacom to go up, even though they likely move together due to an external factor. So here's another example. Assume the following. Assume that cigarette smoking causes lung cancer. Also assume that drinking alcohol doesn't cause lung cancer, not to a significant level anyway. And also assume, and this is just an assumption, it might not be the case, but just for the purposes of this example, that smokers tend to drink more alcohol than non-smokers. Just an assumption. Okay. Suppose we collect the data on elderly people on whom on how much they smoked, X, whether they had cancer or have cancer, lung cancer specifically, Y, and how much they drank, Z, or how much they are drinking. Now, if we run a correlation, because smoking drives up lung cancer as well as drinking in our scenario, if we run a correlation between Y and Z, both of them will move up due to this factor, right? So it'll seem like drinking moves together with cancer, lung cancer, even though we know that drinking doesn't cause lung cancer. So our external factor in this case, that's not in our analysis, causes both of these to go up, and a lack thereof causes it to go down. Okay, relatively, right? So it seems like you'll get a correlation between cancer and drinking, but the one doesn't cause the other. That is why you get the movement, you get the correlation, but you cannot say the one causes the other. Okay? Correlation among several variables. Very important to know that you can only get the correlation between two variables at a time. Okay, we're going to draw up a correlation matrix in eViews a bit later on, but you can only do two at a time. So if you've got three variables, for example, you're going to have three correlation coefficients. You're going to get the correlation between X and Y, X and Z, and Y and Z. Unlike with a multiple regression analysis, which we'll do, where you can ultimately regress as many variables as you like against your dependent variable. If you've got four variables, you'll obviously have a larger matrix. So I'm not going to explain this matrix now. I'll explain it when I do it in X or in eViews. That it's a bit easier to explain there. And so, because we don't have causation or we cannot conclude causation if we've got correlation. We need a regression analysis. And this is a process of constructing a mathematical model or function that can be used to predict or determine one variable by another. Okay? Key issues here when we do regression, and this is the first thing we need to identify, is direction of causation. So in this regard, we'll have two variables, two or more, but we'll distinguish between two groups of variables. We'll distinguish between our dependent variable and our independent variable. So if we think about, for example, the Sasol share price and the oil price, we know that, and we've seen this recently, that the oil price causes the Sasol price to go up and down. So the Sasol share price depends on our oil price. Okay, we know this. So, but the question is, does the Sasol share price affect the oil price? And that is not the case. The Sasol share price does not affect the oil price. Okay? The Sasol share price doesn't have any effect on output or demand, or at least not significantly. No, Sasol does produce some oil, but not nearly enough to drive the oil price. So the oil price got a very strong effect on our Sasol share price, but not vice versa. So our dependent variable will be our oil price. Our Sasol share price. This will be our dependent variable, our Sasol share price, and that will depend on our oil, which is our independent variable. Our dependent variable typically denoted as y, and our independent variables as x, variable or variables. Hope that example makes it clear the difference between our dependent and independent variable. Okay. Now, as I said, we are going to derive our regression line from this scatter plot. And I'll do this in our next video.